Hello, everyone. So we're going to continue on with integrals, and this time we're really going to focus on definite integrals. So we've seen those before, and what a definite integral is as opposed to an indefinite integral. Just as a quick little recap on that, we would have an indefinite integral that we might just write like this, and then we'd have a definite integral where we're going to actually have endpoints here, and we're going to have an a and a b, limits of integration. And the difference here, obviously, is that in the indefinite case, we're going to get an answer that ends up looking something with like a plus c. We're going to get some function and then plus c, and so that this answer is not definite because it can change. Depends on what plus c is. And then here, this is a definite integral because we're actually just going to get a number out for this. And we saw that at the very end of the last lecture. But here, we actually want to, what we're going to talk about today is actually what this number actually means, what that number actually is. And that leads us to Riemann sums. So before I actually talk about what a Riemann sum is, let's actually interpret integrals themselves. And so we've seen before, we've talked about derivatives quite a bit. And we've always said sort of derivative means slope. That's been our big thing. When we use the word derivative, we really just mean slope of the function. Well, when we use the word integral or antiderivative, what we really mean is area. And so in the same way that derivative pairs with slope, integral is going to pair with area there. And so that actually answers this question of this definite integral. When we get a number out, what it actually means, this number that we get out is actually an area. That's actually what it represents. And we'll see here on this next slide I'm about to flip to, that it's the area between a and b of f of x. So let's take a look at this. So let's say I have a function, f of x here. So I've graphed it right there. And I'm mostly just going to focus between a and b. So I don't really care about anything, out here. I don't care about the outsides at all. I'm just going to look in between a and b. And so if I have this integral here, what we can actually look at is we can look at a and b. And so, I've got my tick marks right there for a and b. That's good. And this integral actually represents this green area right in here. And so what I'm doing is I'm basically looking left to right. I'm looking between a and b, and then top to bottom, I'm starting at the x-axis, and then I'm just moving up until I hit the function. And once I hit the function, that's sort of my upper boundary. And so obviously this upper boundary changes. It's not, perfectly straight like these other ones. And so that's what this integral represents. What we might say is this integral is equal to the area under the curve. That's sort of a common phrase you'll hear among mathematicians, and in particular, I'll say it a lot. So area under the curve. And we're just saying, hey, I've got this function here in the red. And if I want to look at the area underneath that, I just go down until I hit the x-axis. And then these limits of integration, these endpoints a and b, that tells me where to start and where to stop. And so that's what this definite integral actually indicates. It actually indicates this area all in here in the green. So that gives us sort of an intuitive meaning of what this definite integral actually stands for. When you see this definite integral, you'd say, oh, cool, it's the area, great. But we want to actually figure out how to find the area, and that's where Riemann sums come into play. So this idea of Riemann sums is going to be actually finding the area. And so let's go ahead and take a look at this. So what I'm gonna do a series of slides, and they're all gonna look pretty similar, but they're gonna slightly change. So first, right here, this is our area that we want to find. So I've graphed the same function here. I've made it a little bit wider, and we're looking for the integral from a to b of f of x dx. That right there is what this function actually, or this green area, that green area is represented by this definite integral that I've boxed right there. So as it stands, that's what that is. We could actually just put that right in the middle there. That's that. And so that's my definite integral. Now let's say that now this is going to be hard, right? This function, maybe this function is complicated. Maybe I don't know exactly what this is. I mean, obviously this region isn't a perfect square or a rectangle. It's not a triangle. It's not a trapezoid. It's not anything that we can easily and definitively state what the area is, because it curves. It just curves in this very weird fashion. So what I'm going to do is I'm going to try to guess at this area. I'm just going to approximate it. And the first way that I'm going to approximate it is I'm going to find f of a right there. And so I'm going to go ahead and mark this here. I'll mark it in gray. And I want to be very careful here. So this is kind of a coincidence here that this function, that at f of a and at f of b are the same. For now, that's fine. We'll see why that's just a coincidence here. I mean, I just happened to draw this function so that these kind of line up perfectly. That's by no means necessary. That's just really just a coincidence here. So we happen to have this f of a and this f of b that are equal. Okay, fine. But really, what I'm doing here is I'm just saying, ignore f of b. Ignore this point over here for a second. I'm taking this point right here, a comma f of a. Go and write that a comma f of a right there. I'm taking that point and I am drawing a line straight across, and that's the top of this green rectangle. This top of this green rectangle is defined by this height right here. It's defined by f of a. And so that's my first sort of guess here. Yet again, what I'll mention, it's a coincidence here. This is just a coincidence. Again, it's just the way I've drawn this function. I could have drawn this function, like this, and it would, and the same thing would apply. I would have my same rectangle that goes all the way across. So basically, we've got f of a here, and this is our height of this rectangle. And you can see that the width is b minus a. It's the difference between a and b. And so what we've got is we have a rectangle and we actually know the area of it. We could actually explicitly write out, ooh, that color's bad. Let's do this. We could explicitly write area is equal to f of a multiplied by b minus a. That's just length times width. I can make that even more clear. Here, let's go ahead and do that. Length times width, which is equal to f of b times b minus a. Or excuse me, f of a times b minus a. I misspoke there. Because this length right here is f of a, and this length right here is b minus a. And so that's my area for this rectangle. Now, when we're looking at this, I noticed something bad here. All of this area that I've put in this highlighted red, that's extra area. That's counted extra. And it's not supposed to be there. I'm just looking for the area underneath this curve. So I should just be looking for the area underneath this highlighted red. And so obviously I'm actually extra counting part of this. I'm actually counting extra all of this here in the purple. And so in this scenario, sure, we can calculate the area, but it's not going to be very good. It's not going to do a very good job because we're obviously all this purple here, we're extra counting that and we don't want to count that. So what we might do is instead of just having one rectangle, we might actually switch to having two rectangles. Or we could even switch to having four. I'm going to go ahead and skip over the two rectangle scenario and jump right here to this four rectangle scenario. And in this scenario, what we see is, again, I have a point here right there, A, comma, f of A. And I'll go ahead and mark that. And what you're seeing me do here is I'm taking this point, this y value, and I am moving across just a quarter of the way between A and B. I'm not going all the way over. That's what we did on that first slide. I'm just going to go a quarter of the way, and then I'm going to stop, and then don't even worry about what happens next. I'm just going to stop right there. And so what this is doing is it's creating a rectangle with a height of f of A and a length that is just a quarter of the way between B and A. And so I end up having this whole rectangle here. And then watch what I do next. Now that I have this first rectangle, I'm going to take this point down here, which I'm going to call this x1. Actually, no, I'm just going to call this smiley face, just to give it a nice symbol that we can refer to. I have smiley face right here. And what you can see is that this point is given by f of smiley face. Let's move that up just a little bit. So I have f of smiley face right there. And what I've done now for the second rectangle is I've taken that f of smiley face, that y value, and I've drawn a line straight across until I go another quarter of the way. Now I'm halfway there. And then watch, once I get to that now second sort of iteration, let's make a frowny face. I'm going to come right here. And again, I'm going to squeeze this in here. F of frowny face. Come all the way across. Once I hit that y value, I'm going to go a quarter of the way again until I get to this point. And then I just do the same thing. Lastly here, let's put just a straight face. No smiling or frowning there. So what I'm doing there is I'm taking this point of the function and I am finding, hey, that point, I can label it f of straight face. And then I just go there. Once I have that point, I just go the last quarter of the way. And there we go. I now have 4 different rectangles. And each of those rectangles has a different height. Each of those heights are labeled right here, actually. And so we can sort of clean this up a little bit. Let's go ahead and get rid of all these dashes. And so if we clean this up, basically what we're seeing here is that these rectangles, we know the height and we know the width of these rectangles. We know the heights are, in this case, it's f of A. In this case, it's f of smiley face. In this case, it's f of frowny face. And in this case, it's f of straight face, right? And then the width of each of these is just going to be whatever b minus a is, but then just divide it by 4. Just do it. Just make it into quarters. And so there we go. We now have the area for each of these individually. And so again, really all of that I just said is pretty much the same thing that we did back here. It's just here we only had 1 rectangle. Here, when we have 4, we're just going to have a whole bunch of different x values. We're just going to have to be careful there. So the question is, though, what's the point of making 4 rectangles, right? We started off with 1, and as we saw, we said, okay, we're extra counting all of this purple region up here. We're extra counting that, and that's bad. And then we said, hey, what if we tried 2? What if we tried 4? Well, take a look at this on the 4. I'm going to count in the purple all of my extra right there. And then in orange, I'm going to count. Ooh, and I'm not done actually. Purple. There's some extra right there. In orange, I'm going to count what's actually missing. And you'll notice this right in here, it's actually missing when it should be there. And then we have some more purple there. And then we actually have some missing right there. And so we've got a combination of purple and orange here. We've got a combination of extra area and missing area. And so what we actually hope here is we hope this kind of cancels out, right? Back on this first scenario, we didn't have any missing area. We actually only had extra area in these regions. And so we were just really overestimating what the actual area underneath the curve was, right? The actual green area that we're looking for. Here, this green area is more than we wanted. Here, what we hope though is that this purple and the orange kind of cancel out. And you can see here, there's probably a little bit more purple than orange. That's fine. But the point is that it actually does a good job of canceling out the more rectangles you do. And so what I'm going to do next is I'm actually going to change this into 8 rectangles. And you're going to notice the extra areas, which I'll label in purple. And the missing areas, which again, I'll label in orange. These actually start to cancel out really well, almost perfectly here. And maybe you could make a guess. You could say, hey, that cancels with that probably perfectly. That cancels with that probably perfectly. That cancels with that, and that cancels with that. I mean, and maybe they don't cancel just right, but they cancel pretty well here. And now watch what I'm going to do next. I'm going to go to 16 here. And so again, you've got these regions here. I'll just put some dots. So you've got extra regions here. And you've got some missing regions right here. And hopefully the hope is that these cancel out. And really what I'll say now is that here I have 16, right? I started with 1, I went to 2, then 4, then 8. Now here I have 16 different rectangles. If you keep going in 16, 32, 64, 128, if you go to infinity, if you make an infinite number of rectangles in here, so you make them really, really, really small, and you just keep on going an infinite number of these rectangles, it turns out that it perfectly gets you the area that we're looking for, which, just as a reminder, we had that a couple slides back. That perfect area was right here. That perfect area right there in the green. So if you do an infinite number of rectangles, basically it's saying, hey, if we zoom in, my rectangles, they kind of just start to look perfect, right? They just kind of perfectly attach right on there, and then these will go down further and further, and you've got all these little tiny rectangles, and they basically just perfectly make this line or this curve. And so going from 1 to 2 to 4 to 8 to 16, the more you go, the better it's going to be. And so that's this idea of actually approximating this integral, this definite integral. So remember, we had this. To approximate this green area, we're just going to make a bunch of rectangles. And obviously, the more rectangles we make, the more math is going to be involved. But on the bright side, the better our answer is. Our answer won't ever be perfect necessarily, but it'll be better the more rectangles we do. So let's go ahead and actually look at an example here. So what I'm going to do is I'm going to take this function. This is going to be a pretty general example. It's the same function that we've been dealing with, and I want to look at this scenario where we have four different rectangles. As we saw, there are 4 sort of important points right here, and they each have their own y values that correspond to them. And so, as we saw before, in order to find the height and width, the length and the width, the height and the width of these rectangles, we actually have to know the values of each of these points, which means we need to know each of these points as well. Basically, there are, in this case, there are 9 things that we need to know. And I'll go ahead and label them in gray. We need to know this right here, this right here, this right here. We need to know B, we need to know A, we need to know F of A, we need to know F of B necessarily. And I'll just go ahead and mark these just pretty loose. actually be like 10, f of b, f of yada yada, f of yada yada, f of yada yada. We just need to know these 5 x values, and we need to know the function values for each of them, the y values that correspond to them. Once we have that, we have each of these widths and we have each of these heights. And you'll notice these heights come up right there. And that's the height of each of those rectangles. And then we just close off the rectangles, nice and easy right there. And so let's go ahead and do that. Let's actually find these heights, these x values first, and then let's go ahead and then find the y values. So luckily, we have an awesome symbol there, or variable if you want, that we can use. So we have a delta x, and this is what we're going to call each of these regions. And what you'll notice is the way that I've drawn this, each of these regions here, each of these highlighted red sections, they are the same length. They in theory don't have to be, but for our problems, and pretty much any time you ever see Riemann sums, they will be the same length. In theory, they don't have to be though, but for us, they will. And so we're going to call each of these regions delta x. And what we have here, which you can hopefully recognize, is that this entire region is b minus a. We saw that before. So if I want to divide b minus a, if I want to split it into 4 different regions, 1, 2, 3, 4, I need to take that b minus a and I need to divide it by the number of regions that I want. And so what we're going to say here is this width is going to be b minus a divided by the number of regions that I desire. In this case, 4, the way I've graphed it. But if you wanted 48 regions, you could do it. If you wanted 16 regions, you could do it. If you wanted 3 regions, you could do it. So n is going to be the number of regions that you want, the number of intervals, we'll call it. So I'm going to go ahead and write that out. N equals number of intervals. And in that scenario, the width of each interval is just the total width divided by the number of intervals that I want. I'm just taking this total width right here and I'm splitting it into n regions. In this case, n is 4. All right, so right there, we actually have each of these widths right here. So let's go ahead. What I want to do is I want to take this graph right here. I'm going to put this on a new slide. All right. So we've got this on a slide right here, and here's what I want to take a look at. Let's say, well, first off, actually, I want to cover up this delta x right here. We're going to cover up a and b. We're going to actually do some values here. All right. So let's say that this is 1 for a and b is 5. We're going to make this really simple. You could probably look at this and just say, hey, 2, 3, 4. Great, we're done. But if we want to actually calculate those, let's figure that out. So we have a formula. We just saw it. It is delta x is equal to b minus a over n. And in this scenario, b is 5. That's our right endpoint. A is 1. That's our left endpoint. And n is 4. And so very clearly, you can see here that delta x is 4 over 4, which is just 1. So what that means is that each of these regions has a length of 1. So if this region has a length of 1, what I can do is I can just obviously add 1, 2, add another 1, 3, add another 1, 4, add another 1, and oh, look, I get right to 5, as we might presume, as we might guess. And so what we did there is a very quick calculation of delta x and figuring out what each of these x values actually correspond to. And we've got all these x values right here now, nice and simple, nice and easy to use. So if we knew now what our function was, what we could actually go ahead and do is let's go ahead and make this. Nah, we'll leave it as it is. I was going to make it bigger, but it's fine. We've got these points right here. Let's get a good color here. Let's get these in purple. So right there, right there, right there, and right there, those correspond to the heights of these rectangles, as you can see. And what you'll notice is that those points are represented by 1, f of 1, 2, f of 2. Obviously, this requires us to know what our function is. In this general case, we don't specifically know what our function is, so we can't state exactly what it is. But it's just f of 1, 2, 3, and 4. And so now we're good. We know we have all of our points here. You'll notice that we don't need to bother with f of 5, because once we get to 4, we go all the way to 5, and then we're done. We finished. We've hit B. We've hit this sort of wall right here, and we're done. We don't care. So I actually don't need to know 5 or f of 5 currently. We'll see it. It'll pop back a little bit later. But for now, we don't really need to worry about this 5. We've got these points right here, these 4 points, and there we go. We're pretty much good, because now that we have those points, we know, hey, the width of each of these is 1. And then after we've calculated all of these points, we now know the heights of each of these rectangles right here. And so now we can just do a very simple, hey, let's just find the area of each rectangle, add them all up, boom, we're good. So let's take a look at actually a slightly more complicated way that we might have to figure out delta x and figure out what all these are in between. So I'm going to do another slide here, and this I'm actually going to graph by hand. So bear with me for just a second. So let's say that we have our axes here. We'll have f of x, get our nice labels there. Let's say that we've got a function. We'll keep it looking somewhat similar to what we've done before. So we've got our function. It kind of undulates like that. I've got an a and a b, and I'll go ahead and label those points right there, just right where they cross. So we've got f of a and f of b. And instead of a and b, let's actually give these values numerical values. Let's say again that it's going to be what do we want to do? Let's say 1 and 7, and let's say that we want to do 5 intervals. Okay, so we want to go ahead and we want to do 5 intervals. So what I need to do is I need to take this region in here and I need to split it up into 5 parts, and just kind of doing that and hoping I get it fairly close there. Maybe we can make that a little bit better. Move those all over. There we go. This is roughly good enough. As you can see, we've got 1, 2, 3, 4, 5 intervals here. And I've sketched them roughly the same distance apart. That's okay, that's good. So we've got our 5 intervals there. And now in this scenario, it's not quite so easy to just list. Like we can't just put 2, 3, 4, 5, because while all of these make sense, the jump from 5 to 7 just doesn't seem to work here. And so we actually have to do a little bit, we have to do our math again. We got to figure out actually what these each are. And so let's go ahead and actually do that. So I'm going to actually move this up, give myself a little bit more room. All right, so we've got that. We've got our function. And then we'll notice here that we also have these values here. So let's go ahead and do this. Let's say we've got delta x, which again, we know that delta x is this distance. It's all of these distances, right? And so delta x is b minus a over n. And when we're looking at this, b is 7, a is 1, n is going to be 5 because we wanted to split into 5 regions. So in this case, delta x is 6/5. Now, what we have to do is we have to recognize, all right, I'm at 1 and I need to get here, which means I have to add 6/5. And so we gotta, you know, hopefully we don't have to pull a calculator, but we got to figure this out. We got to do fraction addition, right? So if I add 6/5 to 1, I'm going to end up at 11/5. And then if I add 6/5 to that, I end up at 17/5, and then 23/5, and then 29/5. And then if you add 6/5 to 29/5, you get 35/5, which is just 7. And so right here, we've done this example again, where we've changed the number of intervals that we're using. And we've actually figured out, we've actually gone ahead and figured out what delta x is, but also what each, what each of these are. Now we can go ahead and we can say, all right, now that we know that, this is going to be f of 1. This is going to be f of 11/5. This is going to be f of 17/5, and so on and so forth, right? They would just keep going. So when we go ahead and we draw our rectangles, which I can do here, I'm going to start at 1 at my a, and I'm going to go up to until I hit the function. Then I'm going to go over until I hit the next interval, if you will. And then once I hit that sort of imaginary wall, I'm going to come right down, and I'm just going to finish it off right there. So we're sort of pretending that there's an imaginary wall on each of these. All right. So, and then obviously here, let's make sure we label this correctly. Squeeze that in there. So again, we'll have an interval here. And let's actually do this. No, that's okay. We'll leave it as it is. So we've got that. Let's do our next wall. So I'm going to start now at 11/5, right on the x-axis. So I'm starting right here. And then I'm going to go up. So it's kind of hard to see, but I'm going up to the function right there. And then I'm going over until I hit that imaginary wall right here. So the moment that I hit that wall, I am now just going to drop right back down to the axis. Now I start at 17/5. So I'm going to start right there where that arrow is pointing. And I'm going to go straight up. I'm going to go straight over until I hit that imaginary wall. And I'm going to go straight down. And then once I'm down here, now again, starting here at this 23/5, I'm going to go straight up until I hit the function. I'm going to go over till I hit the imaginary wall, and I'm going to come right down. And I'm going to keep doing that. Go up, go over till I hit the imaginary wall, and then come down. And then at that point, we're pretty much done. I don't even care about this f of 7 right here, because we've made our approximation where we've hit this end point, we've hit b, so we're done. So we don't even need to know what that is. And so what you've got here are, you've got these rectangles, which I can kind of shade these in, and each of these rectangles, we can calculate the area of them because we already know, well, first things first, we know that the width of each of these is 6/5. That's our delta x, right? And we know the heights of each of these. The heights are whatever f of 1 is, whatever f of 11/5 is, whatever f of 17/5 is, whatever f of 23/5 is, whatever f of 29/5 is. And so that's that right there. We've got that. I can draw some arrows just pointing to each of those. There we go. And so boom, we've approximated the area underneath this curve. And obviously we're extra counting some stuff here. We're not counting, we're missing some of that area. We're missing some of that area. We're extra counting some more, and then we're missing some here, but hopefully it cancels out appropriately. So there's another example with a little bit more complicated delta X. What you'll notice though, basically what I did is I took my, let's pick a good color here. I took my 1 and then I just added 6/5 and I got 11/5. And then I added 6/5 to get 17/5. And then I added 6/5 and I just kept doing this over and over until I hit the end. So keeping that in mind, let's go ahead and look here at this little formula. And I know this looks pretty ugly and complicated, but bear with me and let's follow this carefully. So if we start at A, what I want to do to get to here is I want to add delta X. So when we calculate delta X, B minus A over N. I want to move delta X. So all I have to do is I have to take where I started from and I have to add a delta X. We did that back here. I started at 1 and I added a 6/5 to get me to 11/5. We did it here as well. I started at 1 and I added a delta X, which was 1 as well, to get to 1 plus 1 equals 2. And so that right there, this first point that I'm at right here is going to be A plus delta X. I'm just going to add a delta X in. Well, now when I want to get to the second interval, the second sort of wall, if you will, I now have to add another delta X to where I was before, which is the same as just saying, hey, let's add 2 delta X's to where I started. And then guess what? If we had 3 delta X's to where I started, I end up here, right there. And you'll notice that's what we did here. We had 1 delta X to jump this gap. To jump this gap, we had 2 delta X's. To jump this gap, we add 3 delta X's and 4 delta X's and 5 delta X's. And that just gets us all of our values right there. So really what we have here is, in a formula, what we can do is we can label each of these as X sub I. And I is we say use the letter I for index. So it's kind of like a count. It's like kind of like a counting. It's an indexing. And so what we're seeing here is that each of these X values, it's just, hey, start at A, and whichever one of them you want to get to, add delta X I number of times. So this is I multiplied by delta X. That's a multiplication right there. And then what you end up getting is you end up getting this right here. You end up getting X0, X1, X2, X3, and X4. And remember, what we said was that Xi is equal to A plus I delta X. So when I write X2, for example, that means I is 2. You can hopefully see that correspondence right there. I'm saying I is 2. So that's A plus 2 delta X. And that's exactly what we've done before. We've just basically, I'm just saying, hey, if I want to get here to X2, well, I have to add delta X and I have to add delta X. And that gets me right there. And so there we go. We've got our way that we can find each of these values. And we did it obviously back here. And we didn't really use any formulas or anything, but that's what we were doing, is we were just using this formula and we were just doing it over and over. At this point, as I've said multiple times, the height of the width of each of these rectangles is delta X, right? We have a delta X over and over and over and over. That's good. And then the height of each of these is just given by F of X0, X1, X2, X3, and then you'll notice we don't worry about X4. So F of Xi is our height for each of these, depending on whatever X sub I is. Remember, X sub I is given by this right there. And so there we go. We've got that right there. Let's go ahead and do a quick example of actually finding, basically what I want to do another example of this right here, but I want to do it using the formula. All right, so we're gonna do a simple graph here. Come on. Not really working now. Let's get it straight. There we go. All right, we've got f of x, we've got x. I'm going to label, I'm going to graph a function. Let's make that a little bit more curved. There we go. There's my function f of x. And what I want to do here is I want to actually start right at 0, and I want to go to 7. And so I'll go ahead and label kind of an imaginary wall right here where we're going to stop. That's our last point right there. So what I want to do is I actually want to do 5 intervals again. So we did 5 last time. Let's keep with that. So I want to split this into 5 regions. That's probably close enough. And so when we have this in 5 regions, we got to figure out what the length of each of these parts is, right? We got to figure out each of those. And so to figure those out, we're going to have to calculate delta x. So let's go ahead and do that. We have delta x is b minus a over n, which is going to be 7 minus 0 over 5, which is just 7/5. So what's probably pretty obvious is this first one is just 7/5. If I start at 0 and I add a delta x, I'm going to get 7/5. But let's not jump too quickly ahead. Let's go ahead and actually work this out sort of carefully. So we'll have x naught is always a, which in this case is just 0. So x sub 0 is just a. X sub 1 is going to say, hey, take a and add a delta x to it, right? And when you do that, you're going to get, well, let's actually, I'm going to move this over just a little bit. I'm going to make all this kind of line up, hopefully. A is 0. We saw that. That's our starting point. Delta x is 7/5. So I get 7/5, just working that out. x2 is going to be a plus 2 delta x. Now that I have this written a couple of times, let me be clear. We're using this formula here. We're using xi is equal to a plus I delta x, and we're just changing I. You notice that 0, 1, 2, and there's a 0, a 1, and a 2 right there. And so I'm just changing I each time to give me my sort of new value. 0 is a plus 2 times 7/5 gives me 14/5. x3, x4, x5, a plus 3 delta x. This is going to be a plus 4 delta x. This is going to be a plus 5 delta x. I'm just using this formula in the green in the bottom, from the bottom left. 0 plus 3 times 7/5. 0 plus 4 times 7/5. I know this is kind of squeezed in here, but I'm hoping that it's seeming a bit repetitive and we're understanding what's going on here. I've got 21 over 5. I've got 28 over 5. And then I just have 7 here. And oh, look, that's b. That happens to be equal to b. So x5 ends up being equal to b in this case because we have 5 intervals. And so really, I can now just go ahead and label 14/5. I can label 21/5, 28/5, and then we had our 7 right there. And so this is what I want to point out here. What we've done is we have just calculated, let's pick a color, let's go yellow. We've calculated x0, x1, x2, x3, x4, and x5. So when we go to make our rectangles, we're going to first start at 0. We're going to find the function exactly where that is, which to me, this looks like it's just right at the origin. I'm going to go straight across. You'll notice that just doesn't make a rectangle. It just makes a flat line. So that rectangle just has an area of 0. Then once we hit this imaginary wall, we're going to go up until we hit the function. and then we're going to go over, and then until we hit that imaginary wall, we're going to come straight back down. Now from 14/5, I'm going to go up until I hit the function, go over until I hit the imaginary wall, and then go straight down. Now from 21/5, I'm going to go up until I hit the function, over until I hit that wall, then straight down, and then do it one last time right there. You'll notice that this is actually a very severe underestimate. There's a whole lot of area in here that I'm not counting that we should be. In a perfect world, we would count that. So there's a lot of area there that we're missing. That's okay. We're not going to get into that just yet. For this example, I really just want to focus on, hey, I'm going to use this green formula right here to find all of my x sub I being that indexing that just changes from 0 all the way up to n being 5. Great. So we've got that. As we saw here, just as a quick reminder, we've got delta x. We've figured out how to find delta x. We figured out how to find each of these x sub I. And we've said verbally that we know how to find each of these heights right here. And that would just be taking each of my x's and plugging them into my function. We haven't dealt with a specific function yet, so we haven't been able to explicitly do that, but that's okay. We know how to do that. We know how to find each of those heights. It's just f of each of the x values. So what I like to do here is I like to change the coloring. I like to make it very indicative of which area corresponds to what. And so what I notice here, so I'm gonna try, actually, let's just do all this in a solid black color. So this length right here is delta x. This height right here and I'm going to actually be a little bit more careful there. This height right here is going to be given by f of x naught, because the height, as you can hopefully see, is right there. It's that red dot, and that red dot corresponds to x naught, and that's the function at x naught. So that's that height. Yet again, we've got a delta x right here. We've got a function height f of x1. Again, that dot right there, that second dot that I'm pointing to right there with that red arrow, that second dot right here, that is a height of f of x1. Boom. That so the purple, I guess this says blue. This is meant to be blue. It might look a little purplish to you. It looks a little bit purplish to me. So we'll call it blue. That's okay. So this blue purple area, it has a height given by this dot right here, this point, this coordinate point, which is just f of x1. And then we just keep going on, right? We have a delta x. We have another delta x. And then, as you could probably surmise, we have an f of x2. And we have an f of x3. So we finish that out right there. And so each of those rectangles has a length, or a width and a height, or a length and a width, or a height and a length, however you want to call it. We just multiply those. We just take the f values and we just multiply them by the delta x values, just length or width times height right there. And that gives us the area for each of those. So at that point right there, if that's the area for each of them, then all we have to do is add those together, and that gives me the total area. So what I'm going to do here on the next slide, I'm going to take each of these right here. Let's actually box them. I'm going to take each of these that are boxed, and I'm just going to add them together, okay? And when I do that, I have each of those right here. And I've added them all together. And there's a much more succinct way of writing this. We can use summation notation. So this summation notation, this is a sigma, that this indicates that I'm summing, that I'm adding things up. And what I'm adding up is I'm adding up this, and notice the index I. And what I'm going to do is I'm going to start I at 0, and I'm going to let I go from 0 to 1 to 2 to 3. So I'm just going to count up, and I'm going to each time do this. So I'll go ahead and write this out explicitly. F of x1 Well, we have I, but I'm going to start I at 0 times delta x. Then I'm going to add my next term, which now I is equal to 1. So f of x1 times delta x again. Plus, I'm adding again, because it's a sigma, it's summation notation. So then I'm going to add I is now 2. And then I'm going to add f of I is now 3. And you'll notice that what I've written here in the dark black is the same as what's already typed onto the slide. And so this is just a fancy but a much simpler way of writing out this. It'd be really nice to write this out if instead of having just going up to 3, if I was going up to like 72, if I had a bunch of intervals, if n was huge, that would be key in writing it in this notation here. All of this method that we've done, everything we've been doing is a Riemann sum. I don't really think it's worth, really emphasizing that word. I mean, we'll use that word to talk about it, but everything we've been doing is just basically approximating that integral, just going way back to the very beginning here. We had an integral here and we tried to guess what it was just by making a bunch of rectangles right here. 1 rectangle, 2 rectangle, 4, 8, 16. And so we're just trying to guess at what that area underneath the curve is. And all that whole process is called Riemann sums. All right, so what you may have noticed is that on these examples, we've always started from the left and we've drawn over to the right. Well, I want you to take a look at this for a second. Maybe pause for a second if you need to, but I want you to spot the differences here and how these are different. So you'll notice we have our function that's very similar in each of these. It is the same exact function. And I have the same xi values. So all of these match up. They're perfectly equivalent right there. All of those are the same. And what I want us to figure out here is what's actually going on differently here. And what I see is that in this scenario, my height, basically what I'm doing is I'm starting at x0 and I'm going up to the function. I'm going over until I hit that imaginary wall, and then I'm going down until I hit right back down. And then I do that again. I go up until I hit the function, over till I hit the imaginary wall, and then back down. And then I go up, and then I go right, and then I go down. And then I go up, and then I go right, and then I go down. Over here, you'll notice if I try and do that, that's actually not what's happening. What's actually happening is I'm going from right to left here. So I'm going right. So I'm going to start at x4 and I'm going to go up until I hit the function. Then I'm going to move to the left until I hit that wall. Then I'm going to go down. And then I'm going to start at x3 and I'm going to go up until I hit the function. I'm going to go over to the left until I hit that wall. I'm going to go down. And keep doing that. I'm going to go up, left, down, up, left, down. Versus here, I'm going up, right, down, up, right, down, and then so on. So what's happening here is we're actually doing a left Riemann sum versus a right Riemann sum. And you might be sitting there thinking, wait a minute. When you were doing this, you went up, right, then down. Then you went up, right, then down. Why are you calling this a left? And then over here, I went up, left, and down. And then I went up, left, and down, and so on. Why am I calling this a right? Well, the reason, the naming of this left and right, it has to do with this. Basically, the name comes from answering the question. All right, look in your interval. This is our interval that we're looking at. We're just going to look in between x0 and x1. Where is the height of the rectangle defined by? And in this case, this is my region here that I'm looking at. And the height of my rectangle is defined by the leftmost endpoint in this area. Just let's look in between x2 and x3. So ignore all this over here, ignore all this over here. I'm just going to look right in this pocket right there, just right there. The height of the green rectangle is given by the leftmost x coordinate in this region, in this interval, right there. This is the leftmost coordinate versus here, Ooh, let me draw that a little better. Versus here, you'll notice that the green rectangle height is given by the rightmost coordinate. So that's where that name left and right comes from. Now, let me be clear. What you could do, you could, instead of doing a left or a right, you could actually do a middle. Now, I'm actually going to show this really quickly. So let's go ahead there, 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 there. I have 5 regions there instead of 4. That's okay. That's not really what's important here. Oh no, I have the same number of regions. I miscounted. That's okay, good. So we've got that. So what I could do is I could say, all right, here's my imaginary walls. Let's just let these go up. I'll erase later. I'll erase all the extra later. But let's actually find the, instead of doing a left or a right, I'm going to do a middle, what we're going to call a midpoint. And so what I'm going to do is I am actually going to look in this interval right here. Just look in between these red lines. Just look right there. I want to find the middle x coordinate of that region, which when I see it right there. I'll put a little asterisk. And I also see it right there. And I also see it right there. And I also see it. Let's do that in different color. Let's do that in the gray. So I'm looking at the middle x coordinate as opposed to a left or a right. I'm looking right dead smack in the middle here of all of these regions. And what I'm going to do now is I'm going to make the height of my rectangle equal to whatever that midpoint is right there. These are all fairly similar, but that's kind of just coincidence. All right, let's get rid of some of this extra stuff, make it look nice. I don't know how well I'll be able to get rid of all that. That's close enough. All right, so we've got all that right there. Yay. And that's our region right there. And now what you've noted, what you hopefully can notice is that the heights here are each given by the midpoint x value, as opposed to here, they're all given by the leftmost value. Here, they're all given by the rightmost value in the interval that we're looking at. We're not going to do midpoint. I just show that just to kind of emphasize the difference between a left and a right. But so here, let's just do this. Let's just get rid of all that. We don't need it. That's okay. We're done with that. We have our left and our right here. Left Riemann sum, right Riemann sum. Boom. So we've got that. And let's actually go ahead and look at a quick little formula for each of these. So right here, this is actually what we saw before. From going from 0 to 3 of f of xi delta x, what you hopefully can notice here is that I have f of x naught. I'm just going to label just the y coordinates here. F of x1, f of x2, and f of x3. And so this area is just equal to f of x naught delta x plus f of x1 delta x plus f of x2 delta x plus f of x3 delta x. Versus over here, I have f of x1, I have f of x2, I have f of x3, and I have f of x4. So what you'll notice is the difference here is here I have x0, but I don't have x4. Here I don't have x0, and I do have x4. So a very easy way to change this is to just, and actually let me go ahead. I want to copy all of this over. Give me just a second. So a very easy way to change this formula is just change the bounds of my summation notation. So here I'm saying, hey, start at 0 and just go until I hit 3 and then stop. Here I'm saying, hey, start at 1 and then just go until I hit 4 and then stop. So I'm going from 1 to 4 here, and here I'm going from 0 to 3, right? And so that right there just explicitly tells me, that just explicitly tells me right out what my formulas are for basically, let me go ahead and add this in, for a left Riemann sum and a right Riemann sum. These approximations to the function there. So we've got good formulas for there. Let me be very clear. Well, I was going to say I don't expect you to, but you don't have to use these formulas explicitly. You're welcome to just reason it out. These are rectangles. I trust that, we're calculus students. I trust that we know how to find the area of a rectangle and add those together. So you don't have to use these formulas explicitly. I will. I think they're very useful. I think they're very easy to deal with, but you don't have to use them explicitly. What I want to make very clear here, let's take a look at this. So on a left Riemann sum versus a right Riemann sum, I want to look at the formulas. I'm going to stick to n being 4. That's what we've been dealing with this whole time, really. I'm going to stick with that. Here we have f of x0 delta x plus f of x1 delta x plus f of x2 delta x. And actually, I'm just going to go to 3. So if n is equal to 3, what it turns out, as we've seen before, here I had 4 regions, 1, 2, 3, 4, and I went up until 3. So I went 1 less on a left area. I actually don't want this here. If n is 3, I just want to go up to number 2. But on a right Riemann sum, I don't want to do the first one, and I want to make sure I go all the way to n, which in this case is 3. And so what you're noticing here, hopefully, is the lack of, and we can actually kind of put this in a gray here. So the gray is what's missing from each of these. And so you'll notice a right Riemann sum and a left Riemann sum, they have a lot in common in the middle here. All of the middle is the same. But it's just on a left Riemann sum, we have the first term and not the last. On a right Riemann sum, we have the last, but not the first. And so that's all that right there. That's just kind of a good way of looking at the differences between these two formulas, if you will. So we've got those formulas. I've written those formulas out explicitly here for an n equals 3 case. There we go. One more thing I want to make very clear is that this right here, this value that we stop at, as I said, we were dealing with n equals 4. We had 4 regions on this example. Most of the problems that we've done today, we've had 4 regions. So I went up to 3. So in general, you're going to, on a left Riemann sum, you're going to start at 0 and you're going to go to n minus 1. So if n is 4, you're going to go to n minus 1. And on a right Riemann sum, you're always going to start at 1 and you're going to go up to whatever n is. So we might actually have explicit formulas. So left is I equals 0 to n minus 1 of f of xi delta x, and then a right is going to be I equals 1 up to n of f of xi delta x. So there we go. We've got all that. Now that we've kind of done all this, really all that's left, I just want to talk about sort of steps for doing this, and then I actually want to just work out one example. So when we're doing a Riemann sum, regardless of whether it's a left or a right, we're going to start by making our intervals. So we're going to be given an n, n is equal to 5 or something like that. So we're going to have our intervals, we're going to make those intervals. Then depending on if it's a left or a right, we're going to pick a height for each interval. Got a little asterisk here. I'm going to put some more stuff down here on the next slide. So we're going to pick a height based on whether it's a left or a right. We're going to draw our rectangles, then we're just going to add up the area of all those rectangles. Picking this height depends on if it's a left or a right. If it's a left Riemann sum, the height of the rectangle is given by the leftmost coordinate point of that interval. If it's a right Riemann sum, the height of the rectangle that you draw is given by the rightmost x coordinate of that interval. And if I, maybe said, hey, try a midpoint, the height of the rectangle is going to be given by the middlemost point of that interval. And so there you go. Before we do our last example, I want to mention just one thing. I'm not going to test on this. I just think it's important to mention that if I take my Riemann sum here, so this is my Riemann sum formula. If I take a limit as n approaches infinity, which basically says I have an infinite number of intervals, what happens is that my number of intervals is increasing because I have n going to infinity. So as my number of intervals increases, the width of each of those intervals has to shrink. That goes back to the beginning of this lecture where I changed our number of rectangles from 1 to 2 to 4 to 8 to 16. When we increase the number of intervals, the width of those intervals all shrunk. And as those widths shrink, the rectangles get better and better. They cancel out in a better fashion to the point where when n actually eventually reaches infinity, it exactly equals the integral right there. So we're not going to deal with this as a formula or anything like that, but I think this is important to write out. I think it's important to notice that a limit of a Riemann sum is equal to the integral. That's like a huge calculus fact right there. So I'll say that one more time. The limit of a Riemann sum is equal to the integral. That's a big thing right there. So let's go ahead and actually work out an example here. So I've actually got two examples written here. I'm just going to do one of them. We're just going to do this first one here. And I'm going to try and do this as quickly as possible just to kind of show you how fast you can go through and actually work this out. I'll leave this second example for you to work on your own. So we've got this right here. And this is how the problems will be written. Approximate the integral. Ooh, and that's kind of cut off there. There we go. So approximate the integral from 0 to 2 of square root of 4 minus x squared using left and right Riemann sums with n equals 4. What you'll notice here in this particular example, you actually don't know how to do this integral yet. And so since you don't know how to do this integral, try a Riemann sum. Also because I say approximate the integral and I specifically say Riemann sums, obviously you're going to do that. So just in this case, we happen to not know how to do the integral, but let's go ahead and approximate it. Anyways, so first thing that we're going to do, I'm going to try and graph this. I think a graph is very helpful. It's helped us in the past. Let's try and graph this. And so I noticed that this square root of 4 minus x, that kind of looks to me like if I set y equals square root of 4 minus x squared, I might have y squared equals 4 minus x squared. I have x squared plus y squared equals 4. This to me looks like a circle of radius 2. If I were to actually go ahead and graph this, then because we're just looking, well, actually, let's go ahead and do this. So I'm going to sketch this really quickly. There's our function. But now, because it's square root and it is the positive square root, I actually don't want any of the bottom part. I don't want any of that down there. So we don't need any of that. And then notice that I only care about the interval from 0 to 2. And notice this is 2 because my radius is 2. So I just don't even need any of this either. So really, that's my only region that I care about right there in the red. Let's blow this up. Let's sketch this a little bit nicer. And we'll go ahead and do that. I'm going to go ahead and get rid of this work right here. This should be fairly standard work. We know what a circle looks like. So let's go ahead and graph this nice and big. So we've got that right there. And we know that this is 2 because the circle had a radius of 2. So we've got that right there, yay. And what I want to do is I want to use 4 intervals. And so I want to split this region from 0 to 2 into 4 intervals. So first I'm just going to kind of split it right down the middle. And let's split it, each of those down the middle. You could probably look at this and you could probably very easily figure out what each of those tick marks are going to be. Let's just explicitly calculate it. So we're going to have delta x is equal to b minus a over n. B is 2, a is 0, n is 4. We get 2/4, which is equal to 1/2. So then x sub I, which is a plus I delta x, is equal to a is 0 plus I times delta x is 1/2. I simplify this, it's just I over 2. Boom. We now have formulas for delta x. We have a value for delta x, and we have a formula for xi. So if I go through and I actually work this out, hey, x sub 0 is 0 over 2, which is just 0. X sub 1 is 1 over 2, which is just 1 over 2. X sub 2 is 2 over 2, which is equal to 1. X sub 3 is 3 over 2, which is obviously just 3 over 2. And x sub 4, the last one, is 4 over 2, which is 2, which, ta-da, that's actually equal to b, as this first one was equal to a. So now I can go ahead and I can label 1/2, 1, 3/2, and then I've got my 0 and 2 on the endpoints there. So there we go. We've got our xi's now. We've got each of our x values. So basically, what we have to do here is we now have to figure out what each of these coordinate points are. And so let's go ahead and do that. So let's copy this page. So we've copied all that over. Let me get rid of all this. We already did all that. So we want to calculate each of these green guys, and I'm going to go ahead and label these. Let's do this. Let's label it A, B, C, D, and E right there. So for A, I'm going to do, let's do a different color here. Let's go yellow. F of 0, right? And F of 0 is going to be, well, you can very easily see right there. It's just 2. Explicitly written, it's going to be square root of 4 minus 0 squared, which is just going to end up being 2. For point B here, we'll write C, D, and E as well, because we're going to do all those. We're going to do F of 1/2, which is square root of 4 minus 1/2 squared. If we work all this out, you end up getting square root of 15 over 2. I trust that you can do those handful of steps right there. This one's a little bit easier to see. This is just going to be square root of 3, F of 3/2. So I'm just taking the original function. I'm just plugging in each of my xi's, each of my x coordinates. I'm just plugging each of them in there. And we get all these values. Great. We now have proposed heights for each of our rectangles. So we know each of these to be a height of 2. We've got a height of root 15 over 2. We've got a height, actually, that's not going to look good. Let's not squeeze that in. So we've got root 15 over 2. We've got 2. We've got root 3, and we've got root 7 over 2, and we've obviously got 0 right there. So again, I'm going to copy this page. We're gonna paste this. I'm gonna get rid of all this right here. We've done all that. We've got our y values. Now we've got x and y values. Let's draw our rectangles and let's go ahead and just make them. So I'm going to start at 0 right down here, and I'm going to go up until I hit 2 right there, and then I'm going to go over until I hit the imaginary wall, and then I'm going to come down. Then from starting down in this 1/2 right there, I'm going to go up until I hit the function there. I'm going to go over until I hit the imaginary wall, and then I'm going to come right back down. And then I'm going to do the same thing. I'm going to go up, go over until I hit the wall, go down, and then lastly, I'm going to go up, go over, and then come down. I've got my 4 regions right here. I can very easily calculate these by noting that the height, I can just note the height and the width of each of them. So I'm going to label these A, B, C, and D. So this will be different from the points that we labeled. So we can see the total is just going to be A plus B plus C plus D, which A is going to be given by, let's go ahead and do this in a blue. The height of this rectangle is 2 multiplied by the width, we know to be 1/2. That's equal to 1. The height of B, we know to be root 15 over 2. Multiplied by 1/2. So we get root 15 over 4. I'm going to need a little bit more space here. Let's move all that up. For C, we know the height of that to be root 3 times, again, the width of 1/2. So we get root 3 over 2. And then just following this pattern, root 7 over 2 times 1/2 is root 7 over 4. So now, just to get the total area, I'm just going to add them all up. I'm just going to take 1 plus root 15 over 4 plus root 3 plus root 7 over 4. And if you were to actually, you'd probably have a calculator. If you do all this, you get approximately 3.5. And that's our answer right there. For the left Riemann sum, let me be clear. We've only done the left because remember, in each of these regions, we looked at the leftmost x value and that determined the height. So now what I want to do is, again, I want to copy this page. I'm going to basically do the same exact thing, but I'm going to do it for a right Riemann sum. You'll notice that a lot of the work just carries over. So let's be careful. Oops. This is tough to erase here. I'll make sure I don't erase that white, but it seems like I am. It's okay. All right, let's draw our axes back on there. Let's make that straight. There we go. All right, so we've got that right there. Now for a right Riemann sum, as we said, we're going to start from the right, we're going to move to the left. So what I'm going to do, I'm going to start right here at this point, and I am going to draw a rectangle that goes up until I hit the function. But the problem is I'm already right there at the function value. So I just don't draw any up at all. And I just go straight over, boom, until we hit that imaginary wall. Once I hit that imaginary wall, I go down until I hit the axis. Well, I'm already on the axis. So now I'm at this point right here, and I'm going to go up until I hit the function, and then I am going to go over until I hit that imaginary wall. Then I'm going to go down until I hit the axis. And then now from this point, I'm going to go right back up until I hit the function. I'm going to go left until I hit that imaginary wall. And I'm going to go down until I hit the axis. And then I'm going to do the same thing. I'm going to go up until I hit the function, go over. I'm going to go down. And there we go. Now, what I recognize here is I have an A, I have a B, I have a C, and then I technically have a D, but it's like, it's nothing. D is 0. So let's go ahead and work all these out. D is a height of 0 multiplied by the width of 1/2. That's just 0. A, let's go ahead and look at that. So the height here of A is given by this right wall, which has a height of √15/2. You'll notice I don't even care about this 2 that I'm currently covering up. I don't even care about that 2 right there. So I have my √15/2 times 1/2 is going to be my √15/4. And then for B, it's going to be the √3 multiplied by 1/2, which is my √3/2. For C, it's going to be my √7/2 times 1/2, which is my √7/4. Now let's change the color here to make that match. D we already talked about. I add all these up. √15/4, √3/2, √7/4, and 0. And if I actually work all that out, I get about 2.5, roughly. That's my answer. I want to be very clear, the A, B, C, and D, these are just labeling. A, B, C, and D on this right Riemann sum are completely different from A, B, and C on the left Riemann sum. I'm just trying to do easy labeling. They're completely different from these points A, B, C, D, and E that I labeled, just trying to keep my labeling nice and neat. So we've got left and right Riemann sums right there. You'll notice the work looks almost identical. The only difference there is just that you're looking at the left wall as your height of the rectangle versus the right wall as the height of your rectangle. And that's pretty much it on Riemann sums. There's not really a whole lot more to talk about there. Thanks for bearing with me. I know this was a very long lecture, but it is a very important topic. I'm hoping that going through this last example, it kind of makes it all seem not as bad. Obviously, I've written out all my work very explicitly, but you should be able to see that on most problems, which will be like this, these values were very easy to find. You don't have to go through and write all of that, right? You can probably very easily see, all right, there's 4 regions here, and it's from 0 to 2, so I'm going to just iterate by 1/2. So if you're iterating by 1/2, there you go. Now we just find our function values, and then basically we just take all those function values and multiply them by my 1/2 over and over and over, and then we just add them up appropriately to get a left and a right Riemann sum. So it's really not that bad, although there is a lot to get through there. So as I said, thanks for bearing with me. We're going to go ahead and call that for the lecture, and have a good day.